one more distribution for today. This one comes with its own table. This is known as Students' Tea distribution. Students' Tea was created because Guinness, the brewery, wanted to do quality control on its beer. One problem with quality control is, how does one test beer to make sure that it works? You got to drink it. And if you drink the beer you just made, what can't you do with the beer you just tested? Sell it. And why does Guinness want to sell beer? Because they want to make money. It's kind of how capitalism works. You create a product, you sell the product, you profit off of the product. If in the process of creating the product you have to do some quality control tests and use some of the product, then that's less product that you have created that you can actually sell. And so therefore your profit margin goes down. Welcome to Business 101. Guinness wasn't alone. Lots of companies wanted to sort of figure out how they can test their products at a lower cost. And for consumable products like beer, well, in order to have quality control, you have to take a sample. Aha! Back to stats. The idea of a sample. Last class, when we were talking about the distribution of sample means, we introduced this idea of the central limit theorem, and we talked about how sample size matters. And so I walked through and we looked at the standard error. And the standard error is your variance divided by the square root of n. And we noticed that as n gets bigger, the standard error gets smaller, and that's a good thing. Well, what if you want to have it be really small instead of really big? Standard normal distribution doesn't work so well for really small samples. So we needed a distribution that could handle smaller samples. So a mathematician at Guinness, yes, that was a real job, created the Students' Tea distribution. Why is it called student? Well, he worked for Guinness. He created this distribution. Who owns the distribution? Guinness. So he anonymously published it in a math journal and gave it away free to the world. And goes under the pseudonym student. And so this is Students' Tea distribution. We use Students' Tea in two instances. We're trying to estimate the population. In order to teach you statistics, sometimes I have to just tell you what the population mean is. Well, we don't actually know the population mean many times if the population is really large and diverse and geographically spread out. Sometimes we can only get a sample. Also, we'd use the T distribution when we want to guess about the population. We want to take our sample and make an inference about what the population is. Now, for us, this is going to be pretty easy, because if you look at that table, this should not be something foreign to you. This should look very familiar to you, because at the very top, we have a little curve. We have a shaded area. Where it's slightly different is the fact that the distribution itself, and in the equation to create Students' Tea, the sample size is important. Now, I don't want to scare you by showing you the equation that's used to calculate Students' Tea. I did that once already. I sort of burned that card. I can't scare you a second time with an equation. But what I want to point out is, in that big scary equation that's used to create this bell-shaped curve, one of the variables in it is n, is sample size. And I want to explain to you why. Up here, I have 4 distributions. The solid line is my standard normal distribution. That's the one that we've used all throughout the semester. You have your z-table for with the plus and the minus side. That's the standard bell curve with air quotes. These dotted lines are different versions of students' t-distribution depending upon the sample size. So look at the two. The solid line versus the dotted lines. How are they different? Okay, so when it comes to the hump, or the peak of the curve, right, it's not as tall. So it's shorter. Now, the area of a t-distribution is the same as the area of a normal distribution, 1. So if it's shorter, where did that height go? If the hump got shorter, what part of the curve got taller? Okay, the tails got taller. So we can examine this up here. We see how low the solid line is. And as our n gets smaller, the tails get higher. Does everybody see that? There's an increase in the size of the tails. That's the main difference between the t-distribution and the standard normal distribution. Okay, so if this sheet of paper here, just give it a little fold, represents the standard normal distribution. When we switch to a t-distribution, it gets flatter, and these tails kind of flare out. Right? You're sort of like trying to peek under the tails. They're just getting lifted up just a little bit. How is that going to affect us? Why do we need to pay attention to this? It's still the same shape. Well, we base something on the area that's in the tails. Right? We base our hypothesis testing on the area that's in the tails. So we're going to have to be really sensitive to how much area is in the tails. So when we do hypothesis testing and we find a critical value, if there's more area out in the tails, depending upon the size, what's going to be constantly changing with each example that I give you? What? So if I give you different examples with different sample sizes, what's going to change from example to example to example? Yes, that will change, but for us to test a hypothesis, the critical value, right? So under the standard normal distribution, and if I had 95% in the middle, which put 5% in the tails, what was the critical value of z to reject the null hypothesis? It's a magical number. 1.96. And I knew that if I had 1.96, I would reject the null hypothesis. So what's going to happen now with the t-distribution when I push more out into the tails as the number of observations change? My critical value is going to what? It's going to change, right? If I put more area in the tails, it's going to change. It's no longer going to be 1.96, and it's going to change with each different sample size, and it's going to increase. Okay? So get your t-table out. So this is a little bit different. Okay. Again, I like this one simplest one to use. So for the t-table, it's nice to have a little drawing up top, so it tells us exactly what we're dealing with here. The shaded area in the tail is equal to t something. Each of the columns for the t-table represents a different value for the percentage of the area of the curve that's in there. Okay? So if we use 95% and we put 5% in their tails, what number do I want? Which column do I want for that same sort of procedure? I want the column that has what number next to it? Which one of these 5 do I want to use? What number does that say? No. See these numbers here at the top? Which one's my favorite one? That's going to give me 5% in the tails. No. All right, the one that I want between these numbers to have 5% in the tails, this one. Because how many tails do I have? Right? So I've got 2.5% in each tail. That's this one. That's this column here. Let's say I forget. It's test day. I have test anxiety. I'm just trying not to poop my pants. Got this t-table in front of me, and I forget which one it is. Does that number at the bottom here look familiar? It's 1.96. 1.96, I'm comfortable with that number. I like that number. I've heard that number a million times this semester. It's a special magical number for this class. Use that column. So this table gives us the critical value of a t-score that would equal 2.5% in each tail. That's what this table gives you. Right? It gives you the critical value. A little different than the z-table, where you got to decide what percent you want in the tail, and you have to search for it in the field of the table, and then go over and you're like, okay, I want 1.96. This is just making it a lot easier. It's saying, okay, you want 5% in your tails? A total of 5% in your tails? You want this column. You'll notice in this column, it starts at 12. That's not anywhere near 1.96. Why? Well, that's easy. Let's go back and take a look. At our slide here. Okay. 1.96, let's just guess and say that it's here. Okay. Look at how much area is under the curve, how much higher it is there versus there. It's almost double. And then when you add the two tails together, that's a lot. So we're going to have to go way out here in order to get just a little bit in the tails. All right. Let's do an example. Do young people think they're invulnerable? Yes. I have evidence of this every morning when I drive on campus. I pull in, come up from by the gym. I stop at the stop sign, and I want to make a turn to go into the parking lot. And then I witnessed that coastal students think that when I run over you with my car, you won't get hurt. Because that's the only explanation I have as to why you just randomly walk through the road. Yeah, that's a myth. If I run over you with my car, you're not going to college. If I hit you, I'm going to hit you good. You ain't going to college anymore. All right? My 5,000-pound SUV versus your 200-pound body, I win. And there won't be any other witnesses. Right? It'll be bad. You must be invulnerable because you don't use the things that are designed to get you safely across the street. They're called crosswalks. And you can tell if you're in one by the paint that you're walking on. Okay? Also, when you're in this parking lot right here, don't cut through all the cars. Because when you cut through the cars to walk, I can't see you because you're behind a car. Yeah, you're like judging, like, oh, I'll step out now. Yeah, don't do that. Don't stick anything out there that you want to keep. Okay. So there is this idea that you must, again, I see this every day, right? You're crossing the crosswalk and you're like, ooh, shiny, and you just sort of veer off and leave the crosswalk. You're like, oh, I know I need to stay in this paint here, but my building's over there. And so you take the hypotenuse, which means you take the hypotenuse of the triangle, you're taking the longer path, which means I can't turn because you're in the middle of the road. Okay, rant done. But at least some of you will start using the crosswalk now. Let's ask 17 students, when are you going to die? And let's see if you're optimistic. Typically die at the age of 75. Let's call that our population mean. All right, you got 75 years. When do you think you're going to die? 84. That's an extra 9 years. That's optimism. How did we get our 84 average? Well, we asked 17 students. We have a standard deviation of 8. Do students believe you will live longer than the national average? The person who didn't take this class would answer what? Yes. Why? Yeah, because the sample mean is bigger than the national average. But they didn't take this class, and so they know what? What part of taking a sample from a distribution do they not understand? That they need a large sample size. And one more thing. A, it's got to be a random sample, I'll give you that one. And that their sample mean could be different from the population mean. Why? Because sample means are distributed normally, which means they go away from the actual mean, right? There are lots of ones that aren't even close to the mean. Okay. How are we going to do this? Well, first thing we need to do is make a decision about the null hypothesis. And so how likely is it that we would get this sample mean from a population mean of 75? We need to test whether or not those two numbers are actually different. The first thing we need to do is figure out how we're going to create a critical value. In order to use the t-distribution, you have to calculate something called degrees of freedom. Degrees of freedom are a representation of the sample size. The larger your sample, the more degrees of freedom you have. The most common way to calculate degrees of freedom is n minus 1. Which means your sample size has a minimum size of what? It's the smallest n you can use. What is the smallest sample size you can have? Nope. Because if you have an n of 1, how many degrees of freedom do you have? Yeah, you don't have any. You can't do this if you don't have any. You got to have a degree of freedom. So now what's the smallest sample size you can have? An n of 2. The n of 2 is the smallest sample size you can have and call it a sample. How do you calculate the mean of n of 1? It's just that value, right? You're not even calculating really a test statistic. You're just saying this is what it is. Okay? So you got to have an n of 2 at least. This example, we had 17 students. 17 minus 1 is 16 students. No, 16 degrees of freedom. If you have your table out, put a little star up here, arrow, whatever, just a little, highlight it. This is the column we want. We want the middle column. The middle column, 16 degrees of freedom. Our critical value is 2.120. 2.120. Pretty close to 1.96. But remember, we're dealing with a t-distribution that takes into account the sample size. And so the fact that we have such a small sample means that we got a little extra area in the tails, and we need to account for that when finding the critical value. So where is the 95% in the middle? Our t-score is going to be 2.120. By setting alpha at 0.05, that 5% that we're putting in the tails, our critical value is 2.120. Remember, we do a two-tailed test because we believe that you could be in both directions. It could be both a positive and a negative relationship. It is possible for young people to think that they're not going to make 75 because the planet's going to kill us in like 12 years. 15 years, sorry. 2035, we're all going to die. Yep. The hurricanes and the tornadoes and the microbursts, and we'll all be drowned, sea level rise, planet's going to kill us off. That's a possible point of view in your life, right? I'm not going to make it. Earth's going to kill us. Population's going to eat through all the food, and I don't know. I've seen enough horror movies to know that we just ain't going to make it. Zombies. We're all destined to be zombies. Okay. So it is possible that we could have a lower outcome on life, right? I got about 3 years left. That's it. We will reject the null hypothesis that there's no difference between our sample and the population if our t-score is greater than the 2.12. So let's calculate a t-statistic. Let's find out where our sample is on the curve relative to the hypothesized mean. T equals the difference between our sample mean and the population mean divided by the standard error. The denominator there is a little s. Where does that standard deviation come from if it's a little s? Does it come from the population or does it come from our sample? You got a 50-50 shot. Somebody take one. Why our sample? That's right, so I'm not going to throw anything at you. Why is that right? Because if it were the population, what would it be? Would it be a little tiny s? Nah. It'd be a little tiny something else. It'd be a population parameter, and we denote population parameters by making them into what language? They're fraternity and sorority letters. They're Greeks, right? So that would be a sigma. That would be the little O with a hat on it if it were a population parameter, right? So if in the question I give you this information, right, you're looking for the sample's measure of variance. But it's got a little subscript x bar there. That means it's a standard error. The standard error is when we correct for sample size. And we're acknowledging that our amount of variance that we have in this data is really dependent upon how much data we have. So you just have one little extra step, and that's to calculate the standard error by taking your standard deviation of your sample. Right? So this is the S that you would compute from those 17 students who answered your question, divided by the square root of n. N is 17. The square root of 17 is 4.12. I knew it was going to be about 4 because it's around 16, and 16 is a square. What happens to the standard error as n increases? So instead of 17, it's 100. So if n gets bigger, what happens to this number here? It gets what? Yes. As our sample size gets bigger, our standard error gets smaller. Okay, let's hold on to that for a second. To calculate the t-statistic, we now have the 3 parts that we need. We have our sample size, or excuse me, our sample mean of 84. We have our population estimate of 75, and we have our standard error. The difference between the two means is 9. We divide that by the standard error, and our answer for t in this sample of 17 students was 4.63. Am I happy? I'm really happy. Because what's my critical value? Did we forget already? Is 4.63 greater than 2.12? Yeah, it's like way greater. So I'm out here in the tails. The likelihood of me getting a sample I got a sample mean of 84. The likelihood of me getting that sample mean of 84 when the population mean is 75 is really low. It is unlikely that I would get that. There must be some reason why my sample mean was so different than the population mean. I wonder what that could be. I think it has to do that I asked a bunch of young people how long they'd live. And the young people gave me a wildly unrealistic answer, that they would live an extra 10 years longer than everybody else does. The average estimated age of death for the 17 students in the sample was statistically significantly greater than the population average of 75 years. All this sentence is doing is telling me that my sample really was different from the population. The result of this analysis supports the research hypothesis that people will provide estimates of age of death greater than the average life expectancy in the population. I'm going to put younger people. It's not like I went to a nursing home and be like, how long are you guys going to live already? And they're like, I hope I die soon. All right. When we do this, we're making just a couple of assumptions. The first one is that our sample needs to be a random sample. That's generally an assumption we make when we take a sample. We want it to be a random sample, that we're not sort of choosing the results of our analysis by who we ask the question to. Secondly, the data that we're using has to be interval level or ratio level data. It has to be a number that actually means something. It can't be a dummy variable. It can't be a nominal variable, which is just a number associated with a name. And it really shouldn't be an ordinal level variable either. You can make it work on an ordinal level variable, but it wasn't designed for that. So something that you can count. Age is something you can count. It's a number. It has a lot of range to it. And finally, we assume that the data that we're talking about is normally distributed. And when I say normally distributed, think of bell-shaped. Right? I wouldn't expect that the data is bimodal. There'd be two clear categories. We have a distribution called, we have a distribution to count things. It's called the Poisson distribution. And there's one that's called the zero inflated Poisson that looks like that. That doesn't work on this. A zero inflated Poisson model means that it starts at 0 because you can't have negative numbers. And your most common answer is 0. That's why it's the peak of the curve. That's not a normal distribution. It's got a little curvy shape to it, but it's not a bell curve. You wouldn't want to use a t-test if your data looks like this. Sample size is really important. It's going to come in when we calculate the standard error. So here's an example of something similar. All we do is change the number of observations from n to 20, and n equals 10. So just by doubling it from 10 to 20. Over here we get a t-score of 3.19. Over here we get a t-score of 2.25. This one is not statistically significant. This one is, just by changing the size. We know that. We know that. Okay. So that was the t distribution. Why is it important? It's important for smaller distributions, and we can use it interchangeably with small sample sizes when we're talking about z-scores. For today's class, what I would like to talk about is what happens if you don't have some of this information? What if you don't have the population mean? And all you have is the sample mean. So if you have just the sample mean, you don't know which population mean to compare it to. What can we do? Actually, we can sort of reverse engineer some things. That's the great thing about math, is you just move some things around and you can get a different answer. So what we're going to do today is we're going to take our z-score equation, or our t-score, whichever one, and we're going to move some stuff around, and we're going to solve for that mu. And we're going to get a good guess as to what mu is. This is a more likely real-world scenario. 36 members were asked of the Society of an Industrial and Organizational Psychology, IO-Psych. Anybody know what IO-Psych studies? Workers. We study workers to understand what keeps them happy, what makes them miserable. Here's my favorite example of what IO-Psych is. If you're a company, you should let your workers steal stuff, but you should direct them towards stealing the lower cost items. When I was in college, I worked in a paper mill, and the paper mill understood that when you're around tools and things, that you're a worker, you're going to want some of those things. And they had a choice to make. They had to decide which things were okay to steal. So guess which sort of things that a very dangerous, safety conscious, we don't want our workers to die paper mill decided what you should have free access to and as much as you want. Not paper. Not stuff that would hurt you. The opposite. Yeah, eye protection, hearing protection, skin protection. Basically any sort of safety equipment, you just take however much as you want. So what did that mean? It means I had a lot of safety glasses. I had them in clear and in yellow. I had some really kick-ass, like, wrap-around green ones. They were great. All right, so we all had as many pairs of safety glasses as we wanted to. Gloves. We had as many pairs of work gloves as you wanted. We had thin leather ones. The best ones were the railroad gloves because they were really thick. They went further up on your arm. Chemical suits make great rainwear. So you get yourself a chemical suit and you throw it in your motorcycle and now you have a rain suit. And it's actually a little thicker for the chemicals, not to burn your skin. So they make really, really good raincoats. Right? Ear protection. Both the little foamy yellow things that you wad up and stick in your ear, but also the actual cans that you would put over your ear. So you'd steal those so when you went to the gun range, you would keep your hearing. I still have a pair of those at home from 20 years ago. It made them to last. Any safety equipment you wanted to steal, they just put it by the door. Like on your way out, grab some of this stuff to take home. The stuff they didn't want you to steal, they put in a place called the tool crib. Right? My dad worked at the mill, and he has a socket this big. It's about the size of a grapefruit. That socket would go on a nut that was that big. You can't go to Home Depot and get a nut that has a 3-inch wide head on it. You just can't. Like, that's for taking cranes apart. That was really expensive. That you had to sign out at the tool crib. They also put fasteners like nails and screws. They just put those by the door. They even had little bags like, go ahead and fill up your bag and take it home. Because they bought them in bulk, they didn't really care, but it kept the workers happy. And by stealing the cheap stuff, workers didn't steal the expensive stuff. Now when the mill closed, all the mechanics filled up their tool chests with the mill's tools. So that's why Dad has a 3-inch socket at home. The mill closed, they weren't going to use it anymore. One friend of mine had to get a forklift to lift his tool chest into his truck. That's how heavy it was. Yep, just pile it in there. If you like to study people and the weird shit they do, I suggest IO Psych. Let's see if it make you any money. They surveyed 36 members. They came up with an average salary of $56,000. That works. That's good. Good starting salary coming out. It's a master's degree. The variance was $12,000. You have this information, but you want to know if you should go into this field. Actually, your parents want to know if you should go into this field. Because when I was department chair, the number one question that I got from parents was, what will my son or daughter's starting salary be? And my answer was, it should be enough that they don't have to live in your house anymore. And that's all they wanted to know. Will this person live with me after I pay you a lot of money? No, they can get their own place. And they can be done in 4 years. So you only have to pay 4 more years of them. I'm not giving you the population figures. I don't know what the population figures are. If I knew, then I wouldn't have to have this survey. So what can we do to figure out what we think the population mean is? What we have in our sample mean of these 36 people is known as a point estimate. We have a spot on the distribution. That's what we have. We have a point estimate. That sample mean is 56,000. But if you all go out, get on the internet, and find people with degrees in IO Psych and ask them what their salaries are, and you come back to me and you said, well, my sample of 10 people, their salary is, it's going to be different than my sample, right? We've established that. We're not going to get the same one again. If we're smart, we combine our samples and make a bigger sample. But what we're going to do today is learn how to create what's known as a confidence interval. A confidence interval is a band. It's a fence. It's a, what other things can I describe it as? Let's go with fence. It's our reach. If I am the center of the point estimate, our confidence interval is my reach. It's a boxing term. Guys with longer reaches can be further away from you and punch you in the face. Presumably the boxer with the longer reach has the greater advantage because they can punch you, but you can't punch them because your arms are too short. The NBA values something called wingspan. NBA started the other night. They measure people. They want to know what their wingspan is. Again, what is their reach? How wide of a swath can they defend on the court? Let's call it a confidence interval. It's going to be centered on our point estimate. But we're going to see how far out from that point estimate we can reach. What we're going to try to do is to calculate a probability or a percentage that we're comfortable in saying that the sample mean and the confidence interval we create includes the population mean. So we're hunting for mu. we want mu to be in there somewhere. What is the likelihood that we can find mu in there? Not exactly. What is the likelihood that the there contains mu? How confident do we want to be? How confident do we want to be that our interval contains the population mean? Well, let's just make this easy and say 95%. That way I only have to really memorize one column or one magic number. Let's just go with 95%. If I went with 100% confidence, that really wouldn't be very helpful, right? I am 100% confident that LeBron James will score somewhere between 0 and all of the points in his next game. Does that help you? Parent comes in, Dr. Wood, how much money will my son, daughter make if they enter this profession? They will make somewhere between 0 and all of the monies. I am 100% confident that that's what they'll make. Somewhere between none and all. That covers everything. I'm 100% confident. 95% is basically saying we think we'll be right 19 out of 20 times. That's 95% confidence. We're 95% confident that this interval will contain the population mean. This is how we're going to do it. Bless you. We're going to rework that equation where t equals x bar minus mu divided by the standard error, and we're going to move all the parts around to solve for mu. The outcome is going to be our confidence interval. Sorry. Our confidence interval is equal to our point estimate, which is the sample mean. Right? Think of that as our starting point. We're going to start here. And then we're going to do the mathematical function known as plus minus. Have you encountered the plus minus before? The plus minus means you're going to do this twice. You're going to do it once with the plus and once with the minus. Why? I'm the point estimate. I need to go in the plus and in the minus direction. So I'm going to do it twice. So I'm going to find out what number it is and how far out I'm going to go. Am I going to go out a little bit? Am I going to go out a lot? That's as far as I can go. How far out I'm going to go is determined by t. So the actual t score, the thing we were trying to solve for before, we're going to set the t value that we're interested in. And we're going to multiply that by the standard error. Okay. So let's do that. First thing we do is we have to calculate the standard error of the mean. We have our standard deviation from our sample. So that survey of 36 people we did came up with an answer of $12,000. Seems like there's a little bit of range in the value of a starting person in the field of biopsych. So a lot of people, 68% of our sample is going to be between, what's that, like 70,000 and 44,000. That's not bad unless you're in the 44,000 pile. Like, I like that upper salary, but that lower one might bother me a little bit. But those people went into like government work or something. They're not working for some large multinational corporation. Calculate through $12,000 divided by the square root of 36. That's sweet. Divide it by 6. Our standard error divided by is going to be, well, it's going to be $2,000. So we're still in dollar units here. Calculate the degrees of freedom. Because we have our standard error, now we need the t to multiply it by. Degrees of freedom is n minus 1. 36 minus 1 is 35. If we're doing a confidence interval of 95%, that implies that we're taking 5%. We're going in both directions, so we're going to use that middle column. The one I gave you stopped giving you every number up until 30. So you'll just have to trust me that the critical value of the t distribution for 35 degrees of freedom is 2.042. So if this is my critical value, I'm going to take the 2.042, I'm going to multiply it by the standard error of $2,000. That's going to give me a result of $4,127. And I'm going to both add and subtract that value from my initial point estimate. I'm going to get two different numbers because I'm going to get the upper bound and the lower bound of my estimate. That's what the plus minus means. The lower limit of my confidence interval is $52,000. The upper limit of my confidence interval is $60,000. What I've created is a range of values. So the width of my band about $8,250 is the width of my band. There's a 95% probability that the interval that I created of $52,000 to $60,000 contains the population mean of the starting salary of a master's in IO Psych. I knew nothing about the population. All I had was my sample. But I wanted to have an idea of what the population is. So I take my sample, and then I create a confidence interval around that point estimate. Anytime you turn on the TV and you hear the results of a survey, 55% of the American public believes we should impeach President Trump. That's a point estimate. And then if you look at the bottom of the little thing on the screen, it says margin of error, plus or minus 2.4 points. That's a confidence interval. They're taking their point estimate of the survey result. They're saying this is what the public wants, and then they're telling you how big the band of it is. So if 55% of the public wants Trump to be impeached, and the confidence interval is 2.5%, then we are 95% sure that somewhere between 52.5% and 57.5% of the public wants to impeach the president. That's what that means. Right? That's a confidence interval. They call it margin of error, but it's not. It's a confidence interval. Most likely they're doing 95% confidence. If it were 100% confident, what would the margin of error be? 55 points. Because we'd got to go from all the way to all the way. So when you see a poll result and you see the number, now you'll look to see what the margin of error is, and you'll know what that means. They're 95% confident that the population mean is between those two numbers, plus or minus the actual number reported. What does that mean? Well, support for impeachment of the president could actually be higher, or it could be lower. The media likes to engage in what's known as horse race journalism. The story is who's in the lead. And so with the Democratic primary, Biden had a new poll that showed him in the lead. Well, that's just a survey. It's just a population mean. You actually got to look at the margin of error to see really what's his support. So if somebody has a 2-point lead and the margin of error is 3 points, then there's a 95% chance that the confidence interval actually includes them losing, being behind. So we're creating, from our point estimate, we're creating a range of values. What we are hoping to do is to create a range of values that includes the population mean. So theoretically, there is a population mean. It's mu. We don't know what number it is, but we know it exists. We know that mu is probably normally distributed, so we can draw the distribution. We're creating a band and hoping that when we create it and sort of plop it down, that it lands on mu. If we do it 20 times, hopefully 19 of them will include it. Yep, me too. Forgot to mute my phone. I think I have a simulation where we can sort of see this happen. Let me see if I bookmarked that or not. Okay, so let's do the mean, normal distribution. Okay. What do I have here? I have I'm going to simulate a data set. I'm going to ask the computer to draw from a population where the mean is actually, oh, what's your favorite number? 11. And the standard deviation, mine's 4. Okay. So I just asked it to draw a sample. Give me, from a real distribution with a mean of 11 and a standard deviation of 4, give me a sample of 36 observations. The computer's like, okay. Went through, picked out 36 numbers, from whatever that distribution is. And look, I got it. Let's do it 20 times. All 20 times. So this outcomes over here, this is the actual sample means. All right. The most recent sample, it drew 36 observations from that distribution. The mean was 10. That's the dot. So I just did it 20 times, and we're 20 for 20. Let's do it 100 times. It's like I'm at the gas pump, right? I got to get it right on 100. So I just did the simulation 100 times, and 97 times the interval that I created from that random sample of 36 observations included the population mean. Let's do 200. Getting tired. Just did it 200 times, 195 out of 200. Actually, computer's doing pretty good at randomly guessing numbers. All right, each one I do, we can see the line wiggle, right? Let's see if I can stop on one that missed it. Oh, damn it. Gotta do another one. Come on. It's a stupid touchpad. One more time, and then I'll quit. There we go. That one was close, right? This sample, the sample mean was 12 with a standard deviation of 3. It just missed containing 11 if we created a confidence interval around it, right? So if you take those two numbers over here, a mean of 12, a standard deviation of 3.5, take the 3.5, calculate the standard error by dividing it by the square root of 36. Yep, that's n is 36. Okay. We would calculate a confidence interval, and that interval would not contain mu. Did this help or confuse you more? We're so close to 400. Let's see. Yeah, 95.5. This computer's really good at randomly drawing things. Doing a little bit better than it should. One last thing. This is where people demonstrate that they don't actually know what they're talking about. I'll be at a conference and somebody will put up a confidence interval and they'll say, oh, I'm 95% sure that the population mean is in here. Or the population mean is this. And it's like, no, that's not really what we're doing here. Remember, it's the probability of the interval, not the probability of the mean. So it's the probability that the interval contains the mean, not that the mean is in the interval. And if that doesn't make perfect sense to you, then forget about it. But remember, we're creating the interval. We're creating that little line. And we want to know the probability that the interval is on the line, which is why I did the simulation, so you could physically see it, right, go from green to red. Right? It was the line that moved, not the sample mean, or the population mean. Okay. And again, don't worry about it. This basically says if you know sigma, which you never will, it's pretty much the same thing, but you just use 1.96 instead of the t distribution. Last couple of things to remember, that sample size is really important. So for this example, as our sample size gets bigger, the band actually gets smaller. We have greater precision. So if you're doing a survey of likely voters, you want to get as many respondents as possible. You want your N to be larger and larger and larger, because what happens is that confidence interval will get smaller and smaller and smaller. And your margin of error, which is the representation of the confidence interval, will also get smaller. You'll get a more precise band of what will actually happen. I pay attention to the polls because I understand this stuff. This is interesting to me. That's why I teach it. It's interesting to me. So I pay attention, and one of the things that people don't recognize is confidence intervals and margin of error. President Trump likes to put out there polls that show that he is doing well. The problem is those polls have huge margins of error because they're done by a firm that's not really good at doing what it's doing. So I think he uses Rasmussen a lot. Rasmussen doesn't use large samples. They use like surveys of like 300 people. Whereas if ABC News does a survey, they get like 1,100 respondents. Well, imagine what the sort of band would be with 1,100. It's a much smaller band than it would be if you only use 300. So this is like Rasmussen down here, and they're reporting the point estimate of here. Well, ABC is over here, and they're reporting this point estimate. Like, it could actually be different. Yeah. What is it now?
So they surveyed about 1,600 people.
ABC? Or who's this?
This is the, I can't say it.
Okay.
It's a university. From October 17th to the 21st, they said that the numbers of 65% respondents approved the inquiry, while 43% opposed it.
Right.
The margin of error of 3.9.
Okay. So it could be as high as 58 or as low as 52. But it's still a majority. The problem is when you're doing like a horse race and it's Clinton 41 and Trump 49 and the margin of error is like 5 points. Like, you really don't know. Okay. Last thing I want to show you is something that I just want to show you, but I don't actually ever expect you to do. Just want to show you the wonders of math. So one of the neat things I think about math is that you can get the same answer by doing 8 different things. Really pisses my daughter off when I show her how to do something what I think is the correct way, but not the way her teacher shows her. So when we're dividing a decimal by a decimal, you just multiply everything by like 1,000 and you get the same answer. Apparently that's not what Miss Cap says. Oh well. Great thing about math is you can take an equation and completely jumble it around. And what if instead of knowing what percentage you wanted to, percentage confidence you wanted to have, right? I want to be 95% confident. What if you say, I want my band to be this specific. I want to be within $300 of the salary. You can do that. In that instance, you take the equation and you solve for n. And you ask yourself, how many respondents do I need to have in order to make the band $300 wide? All just by reconfiguring it around. And so you can do that. They show you this in the book, but quite honestly, you don't need to learn how to do this by hand. But it's possible. So I won't ask you a question on this, but again, one of the neat things with math is that you just rearrange the equation, you can solve for something else that's missing. It is possible. Yeah, that's good. That's confidence intervals. Next class, Chapter 9, we're going to do difference of means. And we're actually going to look and start comparing two groups. Starting next week, I will be teaching you the things that I expect to see in your course paper. So come to class.